And let me start with first question. Do you have any experience with secure elements or implementation of the security, the embedded devices? Raise your hands. Oh, cool. So I guess you have experience with the old stuff, or the existing stuff, to be correct, which is security by obscurity. So the title is really addressing the security challenges. So let's talk to that. What's the security challenges we can see, and basically how the open architecture can help. Let me start with the, let's say, quick overview. I will talk slightly about the history of Tropic Square, and it's not because I'm selfish, but it's because I think it's important for the context of presentation, and you will better understand why we do what we do, because it's not really the easiest way or standard kind of implementation, which is obvious, or maybe what we do it might be a bit counterintuitive, so I want to explain the reasons for that. We will talk about why industry needs a secure chips. Also, we'll touch on the main topic, like open versus closed architectures, what are the trade-offs, benefits, and how we can address these. And at the very end of the presentation, I would like to talk about our award-winning auditable secure element. Actually, we've been awarded by Embedded Award last evening. So yeah, it's very, we are proud of that. And the whole team is really appreciate that. So I think it's worth to mentioning that. I will start with Tropic, because Tropic Square, you know, we are a group of engineers and started the company. So definitely getting the name for the entity was a tough task, so let's be clear. Tropic is really important topic for us. We put it to the name to have our vision, because Tropic means truly open IC. And this is what we are working on. Basically, we want to build the alternative to closed source designs where you can't audit, and being able to see what were the design decisions, what motivated these decisions, and honestly, what is the limitation of security in that current implementation? Because I will not tell you that there is something like absolute security or trust us, it's perfectly secure. No, we want to tell you what are the limits of the technology, what we did on the testing, and how we know what the limits are, and make you aware of that. Because in the end, we're building on top of existing stuff, and yeah, there are some certain limitations coming from the physics. So if there is the most important message, apart from award-winning TROPIC01, I would just stay with these slides. Because we are new here, we are new in the market, and we really need to let people know that there is an alternative. And this is really the truly open IC, our solution, which we are really working on very, very intensively. So Tropic Square was funded in 2020, so we will turn, I think, 5 years next week. We are based in Prague, Czech Republic, and really our focus is fabless semiconductor security, so we're building the ASIC, and we want to sell the ASIC. So that's why we're looking for the target markets and supporting our customers to implement better security for their end users and to protect their customers, their businesses, and so on. We did not start the company to be yet another closed source vendor, and even not being just semiconductor vendor because we think it's cool. But there is a bit of history coming back to the Bitcoin hardware wallet, which is, by the way, industry also funded back in Czech Republic. And guys behind the company called Satoshi Labs, they were solving the problem how to make the Bitcoin hardware wallet secure. And they had a perfect solution at the level of open source software, where all these aspects of auditability, transparency really help with improving the security. But there was a problem with the hardware which is running at. So back in the day, they solved critical problem not being on the online environment, which been hacked very frequently. So they created a magic embedded device called hardware wallet. And this device work very well for the initial problem they had. Not be on the online market, being somewhere offline. But later, as the implementation was done on the regular chips, there were some attacks coming in and glitching and simple stuff. And all this story about not documented features from the chip. and things which you basically blind, you can't know what you don't know, and the vendor is not going to help you in this extent. So, there was story to try to find a solution with established vendors, but long story short, we end up building our own company to addressing this challenge. So we believe that the chips industry default mode of operation is really security by obscurity, and clearly it's not enough. The chips are having hidden vulnerabilities and hidden backdoors, undocumented features, which are really putting down the quality of the products in the end on the market. And building secure auditable chips without the needs of the NDA to get access to the implementation data, and empowering the end users for doing their own due diligence and verification, or doing it with help of the community, independent expert and security advisors, can really help to create a new ecosystem, which will be what we call the auditable chips and auditable security. Unfortunately, security is not the default at the chip level. So if you have any chip, any implementation, it's not secure from the perspective of our talks or from the perspective of secure elements. And that's the exact reason why secure elements exist. So basically, security, and I guess you know it from your products, like it's always trade-off. Security goes against usability, and this is something what maybe customers do not like, or even if you will have a super secure solution, might not be usable at all, and it doesn't make sense, because then people will not be using that. And sometimes it's really better to move security a bit and be usable and useful. So really the traditional chip, if you just say, okay, I have a crypto algorithm, I want to implement it, it's easy to do, it will crunch the numbers correctly, it will be fine, but the implementation really leaks the data. So it's the reality of the transistors, switching from 0, 1, 1 zeros, and variabilities in the silicon, which you don't have a perfect power traces. And from these power traces, you can guess, or some people definitely can guess, what numbers are computed. So even if you keep your keys secure, then during the computation on the unsecure environment, you might be leaking the data without knowing that. And that's a reason why you have to take certain effort to make the chip secure, but it goes against the economy of the ASICs. And typically, if you are really targeting the cost of the products, you don't really like the fact that security may mean bigger area or lower performance, and in the end, higher cost of the product. But also, the market, at least what we see, is awakening. There's coming the regulations. We are not necessarily fans of regulations, but in this case, it looks like a momentum in the industry which will force some demand for even transparency. And that's the part that we invite on these activities, because really the coming regulations are about the responsibility of the vendors. If you are putting the device on the market, you have to proactively monitor the security of your solution, inform your customers, and not just pretending like, okay, I just got your money, you got my products, and I don't care anymore. So this is the good aspect. But really all these things means that there is a case for the secure elements. And secure elements really allows us to execute sensitive data in dedicated secure perimeter. When we, say, allocate the small functionality of the silicon to this smaller perimeter, we can better control the environment, we can better control the implementation, we will, by design, limit the attack surface, and also can monitor the environment conditions of the chip during the processing. Countermeasures also require some specific implementation hardening, which might be difficult to be implemented at the regular logic. And in reality, this may also have an impact on the technology node which you are choosing for your ASICs. And to be really flexible, we decided to build this secure element as a standalone device, which can be connected to any microcontroller or device which has to be secured. So we have two options at high level for the architecture. We can select either open, which we say it's new emerging alternative, or we can stay with the status quo, closed and still dominating approach. I already mentioned some limitations, like for the closed one, and probably you you hit that already, or if not, ask your engineering team. They will have a lot of stories how they were trying to get the documentation and how to design the features. So limited documentation, by some definitions, backdoor is undocumented feature. It's not necessarily malicious intent to implement some really backdoor, but even the fact that you have in your design something which is not documented, you're not aware of it, it's a serious problem. Also, legal restrictions imposed by NDAs limits the access to the documentation. Even if you get it, maybe if you are a representative of bigger company, you might not see this as a problem. But smaller players, definitely this is a barrier. And if you sign the NDA, you got the documentation, you got the information, but then you are, let's say, limited on how you can use this information. So imagine a situation that you will find a vulnerability which is threatening your customers, and you are not allowed to communicate that. So security by obscurity, that's what we live in. That's the status quo. It works definitely at some extent, and definitely it works for vendors, but not for the customers. And certification and security evaluations are design-oriented processes. So sometimes the security is demonstrated by some certifications, but in the end, it not necessarily means that the certified device is secure, because there are it depends how the certification is done, and again, these things are not really public detailed informations. So in overall, we think that really the closed approach is limiting the innovations aspect of the certification. When you have to pay a lot of money, huge investment to get it, really incentivize vendors to use the once certified device, don't touch anything, just use it again and again, and that might not be ideal. So really, sometimes you might feel like it's an illusion of security, and kind of trust me bro approach is not working. So what we are working on is really the alternative. I wouldn't say complete alternative. I just really say that we building the alternative, and it will be up to the customers to really recognize that. So what we want to do is really disclose the design details and decisions behind these design activities. This should be known to users because they can help. It can help with their decision how to design the secure system. We're talking about secure element chip. It's a low-level fundamental block at the embedded device, chip on the PCB. But it's not the only place where you play your security stuff. So security as a system is a layer of protections. And if you don't know what is there, you either might be underestimating the other layers or over-designing the other layers. So that's what we want to get on, let's say, in balance. So open specifications definitely enables innovation. We see the huge RISC-V movement. It's not not necessarily open source and free code device or implementation, but really open specifications. So things like we can discuss openly what is the role of the secure element, what type of features should be there, and how we can make them securely. Auditable implementation, that's all about, like empowering end users to understand and independently verify the implementations. Open source compatible. Open source can help, definitely. It's enablement for a lot of auditable aspects. Validation and evaluation data available and reproducible. So we're not there yet, but with our chip, which is just tested in our lab, we're really going to provide a power traces which we captured for our evaluation, and we can give our customers, this is what we captured. Run your own due diligence. Try to see what we don't see, and so on. So this is something what we did not really see possible with the established ecosystem in the industry. And yes, back to the Bitcoin stuff, it's really do not trust, verify. It's a mantra of the Bitcoin environment, but it really works well as well. And in the end, for those in cryptography, you will be familiar with the Kerhoff principles. So Kerhoff principles are really the topics like, Denmark's cryptographer from 19th century said, like, system has to be secure even if it's in enemy hands. In other words, you should not be hiding the implementation. Only secure thing should be the key, which is necessary for crunching the cryptography correctly. And one of the topics which I really believe is the most important is this continuous security evaluation, because this is something where we can build alternative to the existing security schema or extend them, because we might not be really limited by evaluation by certain lab for a certain period of time because they have to jump to another project. We can put the chip into the cloud, get it connected, and test it 24/7 by experts. So really, to be clear, I don't say open. Open doesn't mean secure, but that's really the enablement, and that's important. So, I mean, the fact that we will talk about our implementation and we will open the data or design data, it doesn't solve the key problem. We still need to design it properly and securely, but this really enables the, let's say, feedback about the security and onboarding of the security evaluation from the third parties. So this is our little baby, TROPIC01 chip, tiny 4x4 package, QFN32. It's really the, let's say, standalone secure element, so you can connect through SPI to your microcontroller and start building this secure ecosystem at your PCB or your product. It's a bit of block diagram. You will find it on our website. So I would say from, let's say, from functionality standpoint, there will be no surprise. You will not probably find too much different features there, what you can see on the traditional secure elements, because this is really it. Like, secure element is a toolbox. It's a toolbox to building the cryptographic systems. And what we offer is features like secure key generation, signing, verification of the signatures, secure storage, and with certain technologies like physically unclonable functions, we can make sure that the data are encrypted at the silicon level. So if you have even 2 instances of the chip, you store the same data, they will be stored differently in the memories. So even if you do some attacks like getting the data out of the microscope, you will not see the same data, and it will make harder to data extraction. Also, physical security is very important. So we equip the solution with the, let's say, environment sensors like temperature, low-frequency monitoring, glitch detectors, and also tampering detectors like EM detectors, lasers, and active shield. So really high physical security, definitely designed to be difficult to extract data out of this silicon. Yeah, key value proposition, I would say easy integration with the host. That's one of our priorities. So we designed a secure protocol for the SPI, and to make the integration easy, there is a SDK or API interface, which we call it Tropic CSDK. It's on the GitHub, and we currently supporting platforms like Arduino, RP, Microbus, and we'll probably add more like ESP32 and similar platforms, really in the way to enable designers to quickly connect our chip into their system, hook to the SPI, compile the C code, which is on the GitHub, run the example design, and get familiar with that. Currently, the chip is designed with atomic API operations, so we really focus on simplistic use, and you can just pick up the functionality which you need. If you design your application and you find out that maybe some features might be, slightly differently chained, or you want to combine multiple commands together, it can be done by firmware updates on the silicon. Secure root of trust. Secure root of trust is really the key application, and it's what the secure element demonstrates. So it's there to make sure that your environment is secure, and the trust is rooted. That's why we call it root of trust. Is rooted to our implementation, to the bootloader, which is fixed mask ROM code design in the processes, and then our silicon gets the PKI, gets the identity, and then you can link your device identity to our PKI, or we can customize it for your solution. So really applications like providing digital identity, doing the device attestation, secure key generations, elliptic curve supports, and all this stuff is well, the main functionality and the bare minimum you need to make a system secure and auditable. And we're talking about a chip. So currently it's a chip. It gets a firmware which is designed by Tropic. We call it like default firmware, but it doesn't stop there. So basically we have multiple layers. We have a silicon implementation. Then there is a firmware for the bootloader, and then there is a custom firmware at the application. So really the device is designed for a white labeling and user customization. So if you feel that you need something really specific at your embedded device, or even you like the set of features which we provide, but you would like to have your own API to make the device, looking like your own, eventually having a logo on the device, that's perfectly feasible with our designs.